This lab will take into account the principles associated with an object that is moving at a constant speed in a constant direction over a period of time. We will be using Newton's second law in order to determine a computational model that will be programmed into a GlowScript code and will provide a model that reflects the real-world motion. The real-world motion will be captured in a program called Tracker, which will take into account the x position over time so that we can arrive at a velocity and then answer questions about what the graphs look like, how they compare to each other, and how Newton's second law can be used to determine the forces acting upon the system from the surroundings. Newton's second law relates the net interaction between the system and its surroundings to the observed motion or change in momentum. So in this lab, we will be looking at a ball that rolls across a surface throughout the x position. There will be no change in the y position, and it will be at a constant velocity. With Newton's second law, this can be written as force equals mass times acceleration, but it can also be rewritten in order to contain velocity update and position update. And these formulas will allow us to look at how the positions and the velocity update in order to look at the motion of the ball in the computational model. The systems and surroundings in this model are shown in the Tracker video. The Tracker video shows that the ball itself is the system, and the table and the air, as well as my hand pushing the ball, are the surroundings that are acting as forces upon the ball. So in the Tracker model, you can see a graph that shows the x position as a negative slope over time. And so this shows a linear relationship between these two variables. With these conditions, we can prove Newton's second law, as the previous equation shown for the velocity update states that the velocity final equals velocity initial plus F net over mass times the change in time. And if the F net is equal to 0, then that means that the velocity final must equal the velocity initial. The initial conditions of the system are mapped out in the GlowScript code. So for the ball position, it starts at 0.0913 x position with respect to the set origin. And so there is no y coordinate that is given account. And then the ball velocity is in the negative x direction. And contrasting the real-world data collection, the computational model includes the velocity update and position update formula explicitly in order to look at the position of the ball relative to the initial conditions and to the rate that we have inputted. And we also use the velocity from the Tracker model and use that in our code in order to create a suggested computational model of the motion. And so, comparing the computational model between the observed model, we see that both have a similar slope in their position to time, which suggests a constant velocity, except for the observed model, we have a extreme acceleration at the beginning. And so this can be for numerous reasons. One can be because there was an incline that was not accounted for in the system, and so that caused the ball to move at a faster rate. And then it was slowly zeroed out from its net force to resemble the same velocity that the computational model has. And so this can be a reason for that. What if the x position axis was flipped from positive x to negative x? As we could see from the graph that was shown previously, we see a negative slope, which is obvious because the ball is moving in a left direction, which is in negative x direction if we are plotting with a positive x direction in our graph. And so if we flip to negative x, then that means that it's actually moving in a positive direction in the negative x axis. And so this would cause the slope to become positive. What it means for the model to demonstrate constant velocity is that the system has a net force of 0 acting upon it, but that does not mean there is no force. This can mean that the forces add and subtract to 0, but the forces in total cannot be determined because our computational model, while it is resembling a 0 net force, it is not completely accurate. We would need to assume that there is a slope or that there are air particles interacting with the ball that would create accelerations or frictional forces, and these are just not available to us in our model. And thus, we cannot assume that we can add up and total the forces acting upon the system.